welcome in this new video where we're gonna start talking about the wave equation. So let's take omega domain included in Rn be an open set of boundary gamma. As seen precedently, we denote Q our cylinder by omega times 0 infinity, 0 and infinity being excluded, and sigma equal to gamma times 0 infinity. We consider the following problem: finding a function uxt on omega bar times 0 infinity going to R, such as the second partial derivative of u with respect to time minus Laplacian of u equals 0 on our cylinder Q, which is 27. Then we also have u equals 0 on sigma 28, ux0 equals u0x on omega, and du over dt x0 equals v0x on omega. This is 30. Laplacian described is meant to describe the Laplacian with respect to space variables. T is the time variable and u0, v0 are given functions. The equation 27 is called the wave equation. Now, the operator d squared over dt squared minus Laplacian is sometimes denoted with a little square. It's the D'Alembertian. The wave equation is what we call an hyperbolic equation. When n equals 1, omega equals 0, 1, the equation 27 models the small vibrations of a string subject to no external force. For each t positive, greater or equal to 0, the graph of the function giving uxt for each x in omega coincides with the configuration of the string at time t. When n equals 2, the equation 27 models the small vibrations of an elastic membrane. For each positive time, the graph of the function giving uxt coincides with the configuration of the membrane at time t. Usually, the equation 27 models the propagation of a wave, acoustic or electromagnetic, and so on, in an homogeneous elastic material, omega. The equation 28 is the Dirac limit condition. It can be replaced by the Neumann condition or other conditions we are going to present later. The condition u equals 0 on sigma expresses that the string or the membrane is fixed at the boundary gamma, and the Neumann condition gradient of u scalar n equals 0 on sigma shows that the string membrane is free at its ends. Why? So here in the little scheme I drew, we can see that the extremity are fixed. So gamma, the boundary, is in blue, and our string is fixed on gamma. The string is orange, and so the red line gives us an information where we see u equals 0, and when we go over this red line, u is positive and below u is negative. So this is an illustration for when n equals 1. So we do have here u equals 0 on gamma. Now let's see another example when n equals 2. When n equals 2, we have a membrane surface, a 3D surface. Our membrane can be fixed on the boundary gamma in blue. If the membrane is not fixed on the boundary gamma, then we have the condition gradient of u scalar n equals 0. Here, you can zoom. We see that the gradient of u is perpendicular to the normal in this very point. Here on this other scheme, we see that we have many possibilities for the membrane on gamma if it is not fixed. So u equals 0 is not appropriate. It is not an appropriate condition. The equations 29 and 30 describes the initial conditions of the system. These are the Cauchy data. The initial configuration, we also say the initial movement, is described by u0x, and the initial speed is described by v0x. To set the IDs, we will suppose in the following that omega is of class infinity with gamma bounded. So that's the end for this video. It was just a short introduction, and be sure to stay tuned because a lot more content will be posted very soon. Catch you later. Goodbye.